So what I'm going to do is I'm going to basically go over all the problems you need to be able to do to score well on the kinetics test. So here we go. First thing you have to be able to do is you have to be able to do stoichiometry of kinetics. So here's a typical problem. They're telling me that C is being created at a concentration of 4 molarity per second. And they're asking me, well, what's happening? How much B are you using in the same time period? So what I'm going to do is I'm going to use the ratio of 8 to 5 to figure out what's going on. So what I do is I take my concentration of whichever one they're telling me about. In this case, it's going to be C. I'm going to drop it into the grid, 4.0 meters per second. I'm going from 8C to 5B. So what you notice is moles of C. This is how much moles of C is being created, or molarity. So every 8 moles of C, you use 5 moles of B, and I'm getting that from the chemical equation. So all I have to do to convert it from one to the other using a little stoichiometry is go 4.0 multiplied by 5/8 is going to give me B, 2.5. So I'm using, it's a reactant, so B is decreasing at a rate of 2.5 molarity per second. Question 2, same thing. They're providing with me the concentration that are the rate at which A is being created, or I'm sorry, H2 is being created, 0.030 molarity per second. That's my H2. So then what do I have to do? I'm going to drop that sucker into the grid. Then I'm going to go from I'm producing 3 H2 and I'm consuming 2 NH3s. So what I do on the bottom here is I put 3 moles of H2 on the bottom, 2 moles of NH3 right there. I multiply by 2/3 and I get, bam, I get my answer. 0.020 molarity per second is being used for my reactants. Third one is a sandwich problem. You're definitely going to have to be able to do sandwich problems. That's where you're going to be given a set of data and you have to figure out basically the reaction order. So what I'm going to do is write a generic rate law. Rate is equal to K, concentration of A to the nth power, concentration of B to the nth power. So the first thing I have to do is I'm going to find two reactions where B is held constant. If you notice right there, B is held constant. So I'm going to take reaction 1 and reaction 2. The first thing when I do when I go to use the sandwich technique is find out who's my top bun. If I look right there, 6.0 times 10 to the negative second is larger than 1.5 times 10 to the negative second. So this is my top bun, this is my bottom bun. If you notice, I already have them stacked down here. So if I take reaction 2, or reaction 1 actually is in my top, 6.0 times 10 to the negative second is right here, equals K. Concentration of A is going to be 0.02 to the nth power. Concentration of B, 0.1 to the nth power. Same thing, I take reaction 2. My rate is 1.5 times 10 to the negative second. You can see that right there. K, concentration is going to be 0.1 to the nth, and then 0.1 to the nth power. What I do is I cancel whatever is constant. I'm going to cancel that. So I have to fix that. I'm going to cancel that. I don't know why that keeps happening. So I'm going to just do this. I'm going to cancel this right here. That's actually a point. It's supposed to be a 0.1. That's going to cancel as well. 2 divided by 1, 0.2 divided by 0.1 is going to give me 2 to the nth power equals 6 divided by 1.5 is going to be 4. So that means my exponent for m, the only way I'm going to get 4 is if that's to the second power. So bam, a is to the second power. I found my first order. Then what I have to do is I have to go back and look at my reactions now, and I need to find something where A is held constant. Well, A is going to be held constant in 1 and 3. Now if I notice when I go and look at it, you got to pay attention to the negative exponents. Right there, that's 1.2 times 10 to the negative first. That's actually going to be my top bun, and that's going to be my bottom bun. So what am I going to do? I'm going to take 1.0 times 10 to the negative first. You see it right there. Equals K. 0.2 is my A squared. 0.2 is my concentration of B, and I'm not sure what this is, so I'm going to give that an N for right now. I'm not sure why that says a 1. Then I'm going to take the bottom one. I'm going to take 6.0 times 10 to the negative second, goes right there, equals K. 0.2 squared, 0.1. It's supposed to be 0.1. It's supposed to be 0.1 down there for B. So this is 0.2 over 0.1, and I'm going to end up getting 2 right there. That's going to cancel. If I didn't have it frozen, I could still mathematically solve for it, but I don't need to. So I'm going to just cancel that. So I'm going to have 2 to the nth power is equal to 2. Because when I divide 1.2 divided by 6.0 times 10 to the negative second, it's going to give me 2. So then my exponent for b, or my order, is going to be 1. This would be third order overall. It would be second order with respect to A, first order with respect to B. Sandwich technique. Find your top bond. Same thing with this one, same idea. I have reactance A and I have reactance B. So the first thing I have to do, I'm going to solve for the exponent for A. If I notice, B is already frozen right there, so I'm going to just basically cancel that out, although I do have it over here, so I may as well just. So then I have to look at my reaction rates. If I'm using reactions 1 and 2, I have 21.75 and 7.25. That means reaction 2 is going to be my top bond, reaction 1 is going to be my bottom bond. So then what I do is I'm going to do this. I'm going to basically stack 21.75, you see it right there, equals K, 0.375 and 0.2 goes there. I take my reaction 1, 7.5, 1.25, and 0.3. When I go to do this, this is going to simplify to 3. Come over here, cancel my K's. These are going to cancel. 0.375 divided by 0.125 is going to be 3 to the nth power, which means if they're equal to each other, I know the exponent for A in my rate law is going to be the first order. So I'm going to have rate is equal to K, A to the first order. The next thing I have to do is check B. Well, when I go to do that, I find somewhere where A is held constant. A is going to be held constant in reaction 2 and 3. When as soon as I go to look for my top bond, what do I notice? I notice that the rate stays the same, 21.75, 21.75. If you can't find a top bond and distinguish between them, it means it's zero order. So thus my rate law is rate is equal to K, A to the first. Next one. If you look at this problem, they say the rate constant for a reaction is 4.65 times 4.65 liters per m. So this is basically m minus 1. It's just written backwards. S minus 1. What is the overall order of the reaction? Well, to find the units for K, we always do this. We go m, 1 minus the overall order. That gives us what our exponent is. Well, in this case, our exponent is negative 1. So what does that really mean? Our answer is negative 1. How did we get there? We went 1 minus the order. So a little algebra here, 1 minus what number is going to be equal to negative 1? That tells you the reaction has to be second order because it goes back to this shortcut. So you just plug, you can figure out the order of a reaction. If they tell you the units for K, you can just work backwards algebraically and solve for it. So in this case, I know 1 minus 2 would be equal to negative 1. That's what the order is up there. So I know it had to be second order. Tells you reaction A, when the reaction occurs, A goes to B and C. Study the plot of the natural log of A over time gives a straight line with a negative slope. What is the order of the reaction? This is what you're supposed to be able to do when we do graphical determination. So what that means is you have to be able to memorize the different graphs. Time is always going to be on the bottom. Whenever I have natural log of a concentration and I get a straight line plot, that tells me the reaction is the first order. This relates to exactly what we did in the lab. It's the same thing we got for crystal violet. Question 7. They tell you you have a reaction A breaks down to B and C. The inverse of the concentration of A versus time gives you a straight line plot with a positive slope. Well, time I know is going to be on the bottom. Whenever I have the inverse of a concentration, that tells me that it is a second order reaction. So you have to know all three of them. Graphical determination. Next one, 8. Reaction is first order overall and first order with respect to reactant A. So when I go to write out the rate law, I know rate is going to be equal to A, basically the first order. It says, what is the result of doubling the initial concentration? Well, all I have to do is pop whatever they tell me into the brackets and use the exponent. 2 to the first power, or the first order, is going to be 2. So that means my initial rate would be double. Next one, 9. Decomposition of hydrogen peroxide is a first order process, and they tell me the rate constant right there, so they give me K. How long will it take for H2O2 to drop from that to that? That tells me it's the integrated rate law for first order. So just remember, A at time 0 goes on the bottom. A at time t represents the leftovers, equals negative k times t. Don't forget the negative. I drop my k in right there. Make sure you have the negative sign. They tell me my concentration, that's my initial concentration, is going to go on the bottom, 0.0200. My leftover concentration is going to be 0.0120, goes on the top. And mathematically, you just plug that into your calculator and solve for time. The units for K are in minutes. Notice your answer choices are in minutes, so you don't have to worry about the units. 10. Cyclopropane is converted to propene in a first order process. The rate constant, so they give me K, is right here. If the initial concentration is that, what will its concentration be after 22 hours? Same thing, it's going to be the integrated rate law. This is my initial concentration, which means that's going to end up down there. So I'm going to plug in my initial concentration right there. They're telling me K is 5.4 times 10 to the negative second. I pop that in for K right there. Notice my units are in hours, and they want to know what the concentration is going to be after 22 hours. The units of time match. I plug it in there, and then I'm algebraically solving it and solving for x. Make sure you multiply this side first. To get rid of natural log, you would e this side after you multiply it, and you'll end up cross multiplying, and that should be your answer. Next one. Rate law for the reaction is equal to rate is equal to K with a rate constant of 0.0447. What is the half-life of the reaction? Just so you know, this equation is provided in your AP booklet. For first order reactions, you can solve for K or you can solve for half-life because it's always equal to this. You'll have it right there on your AP booklet. 0.693 divided by K, or the rate constant, is equal to half-life. So in this case, they're telling me what my rate constant is. So how do I find half-life? I just go 0.693 divided by 0.0447, and bam, I get 15.5 hours. If they gave me half-life, and they told all I would have to do in that case is to basically take 0.693 divided by half-life equals K. You can solve for either one on a problem, so be aware of that. It's in your booklet. Next one. Reaction is first order with respect to methyl isocyanide. If it takes 10.3 minutes for exactly 1/4 of the initial amount to react. So if that's how much reacts, what are my leftovers? Because that's what we're always asking in the integrated rate law. I have 75% left, so I'm going to drop 75% on the top. I started with 100%, natural log over here. They're asking me to solve for K, which is unusual. This doesn't happen very often. And the amount of time it takes is 10.3 minutes. So I'm going to plug that down there for my T of 10.3 minutes. When I solve for K, I'm going to obviously find it in minutes because my time is in minutes right there, and that's what they're asking me for, just a little math after that point. Next one, half-life. You guys are asking me about half-life problems. Here's the easy way to do half-life. You write 100, 50, 25, 12.5, 6.25. Notice the numbers decrease by half each time. So if I have one half-life, the definition of a half-life is the amount of time it takes for a sample to decrease by 1/2. So I go 100 to 50 is 1 half-life, 50 to 25 is 2, 25 to 12.5 is 3. After 4 half-lives, you go from 12.5 to 6.25. This tells you the amount that's left over. In the problem here, they're saying, hey, I go through 4 half-lives, so I'm right here. I have 6.25 basically percent left over. What fraction was consumed? Well, if what fraction would be consumed is about 94% at that part, and that's why A is the correct answer. So if you have to solve a half-life problem, just write this little quick solve method on there, and you can click off the number of half-lives. Easy. Next, considering the following mechanism for the oxidation of bromide ions by hydrogen peroxide. So this is basically a mechanism problem. What's weird in this problem is this is actually one piece. It looks weird because it's like H2O plus arrow, or not even an arrow, dash OH. This is one piece, so technically this is an intermediate. So I'm going to cancel that. HOBR is an intermediate. I'm going to cancel that. And I think that's it. There's no more other intermediates. And they're asking me what the overall reaction would be. So I would go H plus. So I would get 2H plus, you see right there. I gather like terms on the same side. So Br minus right there. And then H2O2 goes on the other side. It goes on the same side. Bam. What's left on this side is Br2 and 2H2O. When you total the overall reaction, you cancel the intermediates. That's actually all one piece. That's why the problem's kind of weird. Here, consider the mechanism right here. Which rate law is consistent with it? Well, same thing we just did. HOBR is a intermediate, and H2O plus minus OH is an intermediate as well. So when we go to write the rate law, we always write the rate law based on the slowest step. Here is my slowest step right here. It's labeled. So when I go to write the rate law, I'm going to write rate is equal to K, concentration of H2O plus, arrow or whatever, OH minus, and then Br minus. But this is this is an intermediate right here. That cancels. So what I have to do is go up to the previous reactants, and I'm going to sub those in. So that means I'm going to sub in, oops, not for Br, my mistake. For this, my intermediate, I'm going to sub in H plus and the concentration of H2O2 to the first, bringing my rate law equal to H2O2, H plus, and Br minus. So whenever you have to sub in for an intermediate, you take the reactants from the reaction above. Next one, what is the molecularity, or the number of molecules in the elementary reaction? They're asking you how many molecules are reacting. So I look at my reactants, and I notice that has a coefficient of 1, that has a coefficient of 1, so it's bimolecular. It's just asking you the number of molecules reacting. Most chemical reactions are bimolecular, meaning there's two molecules are slamming together. If it's unimolecular, it would only be one, so it would be A arrow to like B, C. That would be unitermolecular, means you would have 3 or more molecules colliding at the same time. Which of the following affects the activation energy of a reaction? There's only one thing that really affects the activation energy, that is a catalyst. If you take a graph, normal reaction coordinate like this, if you add a catalyst, what a catalyst does is it lowers the activation energy. Activation energy is represented the distance from the reactants to the top of the hill. So if you add a catalyst, what you're doing is speeding up a reaction by reducing its activation energy. 18. Catalyst accelerates a reaction. It's lowering the activation energy. It provides for an alternate pathway. So it reduces the amount of energy required to start a chemical reaction. 19. Reaction of nitrogen monoxide with hydrogens representing the equation. Here's my rate law right here. Notice it's second order with respect to NO, first order with respect to H2. If I triple NO, well, it's second order, so I'm going to go triple it. And then the exponent is 2, and I double H2, so I put a 2 there. Notice my exponent or my order is 1. Well, how much is it going to increase by? What's my rate going to do? Well, if I square 3, I'm going to get 9. 2 to the first power is going to be 2, so 9 times 2, the rate will increase by a factor of 18 times. So if they give you one of these problems, all you do is you have the exponents, you plug in the values, use the exponent to figure out what mathematically happens. That's the whole point of a differential rate law. 20. Which of these changes with time for a first order reaction? Well, time, the rate of reaction will always decrease over time because you're going to have less collisions because there's less concentration of reactants. The rate constant is constant unless you change temperature, so that will stay the same. And the half-life of a first order reaction always stays the same as well. So on a graph, you'll notice that it'll be consistently the same over the scope of the graph. As you go from one side to the other, you'll notice half-life doesn't change. Experimental data from reaction gives these three graphs. Which is the most likely order for this reaction? Well, I know time's going to be on the bottom. What I do is I look at what's on the y. It's the natural log of A. Got a negative slope with a straight line. That tells me it's a first order reaction. Next one, 22. Which of the following statements about the activation energy is true? The activation energy is the minimum energy required for a reaction to occur. So that's the minimum amount of energy to break the chemical bonds in order for a reaction to occur. The slowest step in the reaction is called the rate determining step. Usually has, or it does have, the highest activation energy associated with it also. Next one. For a first order reaction, the half-life is 150 minutes. What is the rate constant? It goes back to this. T1 half is equal to 0.693 over K. Well, they tell me the half-life is 150 minutes, so all I have to do is I'm going to plug 150 minutes in here, and then I'm going to do a little cross multiplication. So all I'm going to do is go 0.693 divided by 150 minutes, and bam, I can solve I can solve the rate constant K. Just this equation's in your booklet, so you don't have to memorize it. 25. The rate law of a certain reaction is what? And they're asking what the unit of K is if you're measuring time in seconds. Well, what's the overall order of this? This is first order with respect to A. This is second order with respect to B, so it's third order overall. So I'm going to do the 1 minus 3 with the molarity, and then it's going to be per second. So that means I'm going to be m negative 2, s negative 1. Definitely have to be able to find the units for K. Rate of a chemical reaction between A and B is found to follow the following rate equation. So A is to the second, B is to the first, where K is constant. If the concentration of A is halved, so we're doing this, but notice the exponent is, or the order is 2. What should be done to the concentration of B to make it go as the same rate as before? So we want to keep it at 1, basically. Well, what's going to have to happen is, in order for you to do that, you would have to quadruple the concentration of B, because if you square 1 half, you're going to get 1/4. 1/4 times what number is going to be equal to 1? You would quadruple the amount of B to keep the rate exactly the same. 27. The rate of reaction 2A plus B products is consistent with the equation right there. Which reaction mechanism is consistent with this information? So it's first order with respect to A, first order with respect to B. So what we have to do is we take each of these and find the slowest step and write the rate law. So the first one tells me this is my slowest step. So when I go to write the rate law, that's the only time you can use coefficients. Otherwise, remember, the exponents are always determined by experiment only. That's why we have the sandwich problems, like problems 3 and 4 on the review. So I'm going to go rate is equal to A to the first and B to the first, and that is the correct answer because it matches the rate law. Very similar to the free response problems we did. 28. Which energy diagram represents a highly exothermic reaction? Exothermic means it's going to decrease. And notice there's a large decrease there. Has a small activation energy. That means the distance from the reactants to the top of the hill would be very small. This is endothermic. That would be endothermic. This is exothermic, but notice it has a large activation energy. The distance is right there.